Yellowstone is a long dormant but restless volcanic system. Lots of earthquakes, significant ground deformation, magmatic gas emissions, heat emissions. This geologic restlessness, which at almost any other volcano would be alarming, this is the norm. That's just Yellowstone being Yellowstone.
Hello, everyone, and welcome to another episode of Eyes on Earth, a podcast produced at the USGS EROS Center. Our podcast focuses on our ever-changing planet and on the people at EROS and around the globe who use remote sensing to monitor the health of Earth. My name is Jane Lawson, and I'll be hosting today's episode, where we're talking about the use of thermal remote sensing in the Yellowstone National Park area and other science benefits of thermal remote sensing. Greg Vaughan with the USGS is the remote sensing lead for the Yellowstone Volcano Observatory and research geologist for the Astrogeology Science Center. Greg uses nighttime thermal views from both the Landsat TEERS sensor and Terra's ASTER sensor to monitor for changes in temperature at thermal features in the Yellowstone National Park. Greg is here today to tell us more about his work and why it's important. And then we'll hear more about Landsat's thermal uses from Terry Sohl, head of science at EROS. To begin, welcome, Greg, to Eyes on Earth.
Hi, thank you for having me.
Just to be clear, you don't work for the National Park Service, but rather the USGS Yellowstone Volcano Observatory. What does the observatory do, and what does your role involve?
Yes, that's right. I work very closely with the National Park Service, but I work for the USGS Yellowstone Volcano Observatory, and my duty station is at the Astrogeology Science Center in Flagstaff. The USGS has 5 volcano observatories that are tasked with monitoring the approximately 170 active or potentially active volcanoes in the U.S. and in U.S. territories. The Yellowstone Volcano Observatory monitors the Yellowstone magmatic and hydrothermal system. Yellowstone is a virtual observatory. There is no physical central office location. We have people located in many different places. YVO is a consortium of 9 different organizations, including the state geological surveys of the 3 states that Yellowstone touches, Montana, Wyoming, and Idaho. We have partners at Montana State University, University of Wyoming, University of Utah, EarthScope, and of course the National Park Service and the USGS. Additionally, the USGS arm of YVO is also responsible for monitoring and reporting on any volcanic activity in the Intermountain West. For example, if there were ever renewed volcanic activity or unrest at one of the 4 corner states. But obviously the main focus of YVO is to provide monitoring and hazard assessment of the volcanic hydrothermal system in Yellowstone and earthquake activity in the Yellowstone region. And we conduct research on volcano monitoring methods and techniques and fundamental scientific research just to better understand the volcanic and hydrothermal system in the Yellowstone region. In my job, in addition to spending a lot of time looking at Yellowstone, I also support other volcano observatories. If there's ever any activity at volcanoes in Hawaii or Alaska, I also will look at data to help support monitoring efforts at those volcanoes as well. My role as the remote sensing lead at YVO is to conduct scientific research using remote sensing tools, and specifically in the area of mapping, measuring, and monitoring Yellowstone's thermal areas. And secondly, should there ever be an event that we need to respond to, help facilitate use of remote sensing data and share remote sensing data products and interpretations that will aid in event response. But my day-to-day task is to use various remote sensing tools to characterize and monitor Yellowstone's thermal areas. And I can add that there are multiple remote sensing data sets that I use. I use the Landsat 8 and 9 thermal infrared data, also thermal infrared data from the ASTER instrument. I'm particularly interested in data acquired at night. I also use high-resolution visible near-infrared commercial satellite data and high-resolution visible and near-infrared data acquired from aircraft, such as from the NAPE program. That's the National Agricultural Imagery Program. I use data from that program, which are also available from EROS. And over the years, the National Park Service has conducted airborne thermal imaging surveys, and recently they've started to use drones to acquire some remote sensing data over specific areas in the park.
Can you give us a little background about the hot water at Yellowstone National Park? How does it get hot and then come to the surface?
Yeah, so beneath Yellowstone, there is a large reservoir of magma that is still very hot. No magma has worked its way up to the surface in about 70,000 years, but it's still hot down there. There's still magma reservoir down there, and it's continually being fed by heat from below this hot spot deep in the mantle. And don't think of this magma reservoir as a big ball of liquid rock sitting down there. It's more like a crystal mush, a hot crystal mush that's really about 85% solid with only about 15% melt. And those melt zones sort of exist as little isolated lenses within this rigid but very hot magma reservoir. And it sits about 5 or 10 kilometers down there. And it's the heat source for this big hydrothermal system. It's what heats up the rocks at depth and drives this hydrothermal system. So rainwater and snowmelt infiltrate into the ground, and they percolate deep down into the groundwater system. And this cold groundwater circulates down, and it gets heated up by the magma reservoir and the hot rocks that the magma heats up to pretty high temperatures. And this heated water also picks up some chemicals from the rocks that it reacts with at depth. It also mixes with some magmatic gases that are venting from the magma reservoir. And this hydrothermal fluid rises buoyantly back up to the surface. Now, if the hot water reaches the surface, we see it as hydrothermal features like hot springs and geysers. And as the hot fluid emerges at the surface, it cools, and some of the minerals that it has dissolved into it, like silica, it has a lot of silica dissolved into it, picked up from the rocks below, it precipitates out, and you get these silica center deposits and silica mounds around geysers.
We're familiar with the fact that Old Faithful is a geyser. What are the other types of hotspots that you see at Yellowstone?
So Yellowstone contains the world's largest concentration of thermal features. There are hot springs, geysers, mud pots, and gas vents, which are also called fumaroles. And there are more than 10,000 of them scattered throughout the park, spread out over a pretty huge area. Now, geysers are a special type of hot spring where there is a constriction in the underground plumbing system that allows pressure to build, and sporadically it gets released in an eruption of hot water and steam. And so these hot springs and geysers are the places where the hot water up to boiling temperatures makes it up to the surface. And by the way, there are only about 1,000 geysers on Earth. Half of them are in Yellowstone, which is pretty amazing. And also, geysers like Old Faithful that erupt on a sort of a regular, sort of predictable schedule, those are pretty rare. Most geysers erupt episodically. It's the ones that erupt regularly that are kind of unique. In other places in Yellowstone, usually higher elevation areas, the hot water that's coming up boils deeper underground before it reaches the surface. And so it's just the gas phases that get separated from the liquid at depth that work their way up to the surface. And these hot gases, mostly water vapor, also have a lot of carbon dioxide and hydrogen sulfide, that stinky, rotten egg smelling gas. These gases tend to be acidic, and they react with the rocks below, altering the minerals in the rock. It really beats up the rock and breaks them down into clay minerals. So at the surface, where you have these gases making it up to the surface, if there's a little bit of water there, you get mud pots, these boiling mud pots. And if it's more dry, you tend to get these gas vents, which we call fumaroles. And these are all generally very hot, boiling temperatures at the surface. And sometimes you see bright yellow sulfur crystals forming around these fumarole vents.
Do you mind explaining a little more about thermal imaging so people who might not be as familiar?
I use available thermal infrared remote sensing data sets to assess and update thermal area maps in the park and identify changes to thermal areas. I also use these data to make thermal anomaly maps and identify differences in heat output within and between different thermal areas. And I also use these data to quantify the radiant geothermal heat output from different thermal areas for the entire region and how it changes with time. And by the way, the total radiant geothermal heat output of Yellowstone from all the thermal areas combined ranges from about 2 to 3 gigawatts. And that's been pretty consistent over the last decade.
Do you want to tell us why Landsat is good for looking at these kind of features and how it's important to your work?
Yeah, sure. So how do we take the temperature of Yellowstone, right? So one way to take the temperature of Yellowstone's thermal features is just to walk up to a feature and stick a temperature sensor in it, like a thermometer or a thermocouple. But like I said before, there are thousands of these thermal features that are spread out over a large, mostly inaccessible area. So it's not really feasible nor would it be very attractive to have little temperature sensors and data loggers stuck into every single one of these thermal features out there. Fortunately, there is another way, thermal infrared remote sensing. So every object that has a temperature emits energy into its surroundings in the form of electromagnetic radiation. And the characteristics of this emitted radiation are primarily a function of the object's temperature. And this dependence on temperature can be described mathematically and is used to estimate the temperature of objects remotely. And without realizing it, we've all kind of observed this before, this phenomenon. If something is hot enough, like an active lava flow or an electric stovetop, it glows with light that we can see with our eyes. This is called incandescence. But if the temperature is lower, like it's not hot enough to glow with visible light, it can still be hot enough to burn you. If you've ever held your hand over a stove that's cooling off, you can feel the heat with your hand, even though you can't see it glowing anymore. You can tell with your hand that it's still warm enough to burn you, so you know not to touch it. And that's because at those high temperatures, it's still emitting light, but it's not emitting visible light. It's emitting light in the infrared region of the electromagnetic spectrum. And so a pot of boiling water or a hot spring in Yellowstone is also glowing, but it's glowing in the thermal infrared region of the spectrum. We can't see it, but we can feel the heat with our hand. And even though we can't see thermal infrared radiation with our eyes, we can build instruments that can see it, like thermal infrared cameras. And these instruments act as extensions of our eyes and allow us to see the world in a new light, literally. And we have handheld thermal infrared cameras, and we can build thermal infrared sensors that we can put on aircraft and spacecraft. And using those technologies is how we can measure the temperature of the surface remotely. There are a number of satellite instruments in orbit that measure emitted radiance in the thermal infrared. Many of these instruments are looking at very large areas, and they have really big pixels, 1 kilometer pixels, 750 meter, maybe half kilometer pixels. And these instruments produce images that cover very large areas, and they're really great at measuring the surface temperatures over these very large areas and or very hot things like fires and lava flows. In places like Yellowstone and hydrothermal systems at other volcanoes, thermal areas can be small and isolated, and at most, they're boiling at the surface. And the amount of heat being emitted from the surface is pretty subtle by comparison to something like a fire or a lava flow. And so they're much more difficult to detect and characterize. So instruments with higher spatial resolution thermal infrared channels are really needed. Landsat 4's thematic mapper instrument, which was launched in 1982, was the first, I think, moderate spatial resolution thermal infrared imager in orbit. And it had one channel measuring thermal infrared radiance with 120 meter pixels. So about an order of magnitude finer detail than some of the other satellite thermal infrared sensors that were available. And then a couple of years later, it was followed by the nearly identical Landsat 5 thematic mapper instrument. And so one of the things that I have done is I've gone through the Landsat archives and I've looked. The first several thermal infrared images acquired over Yellowstone were cloudy. But on May 8th, 1984, this was the first clear thermal infrared image that was acquired. And then on January 6th in 1985 was the first clear nighttime thermal infrared image that was acquired. And in both images, you can really clearly see thermal emission from many of the larger thermal areas in Yellowstone. And so that's where it all kind of started. Then in 1999, 2 new thermal infrared satellite instruments were launched. The Enhanced Thematic Mapper Plus on Landsat 7, which had 1 thermal infrared channel measuring radiance with 60 meter pixels, and Aster on the Terra satellite was also launched in 99, and it had 5 thermal infrared channels measuring radiance with 90 meter pixels. Aster was actually the first multi-channel thermal infrared satellite sensor designed, at least in part, with volcano monitoring in mind. And today there are a handful of thermal infrared satellite sensors with this moderate spatial resolution, soccer field sized pixels, including Aster and the thermal infrared sensors on Landsat 8 and Landsat 9. And there's also an instrument on the International Space Station called EcoStress, which is another multi-channel thermal infrared sensor. So these soccer field sized thermal infrared pixels can see a lot. Most of Yellowstone's thermal areas, even the ones that are not that big and not that hot, are detectable, especially using data acquired at night and in the winter. And this is when we have the greatest thermal contrast between thermal areas and the cold background. So I tend to focus on the use of thermal data acquired at night and in the winter. And this is why I love Landsat 8 and 9 so much. These instruments acquire data regularly not just during the day, but they can also be tasked to acquire data at night on a regular basis. And this is really critical for my work. And over the years, I've been working with Chris Crawford and the Landsat team to make sure that places like Yellowstone and other volcanic targets are on the list of sites where we can get regular nighttime data acquisitions. And this is amazing. And so the other thing about Landsat 8 and 9 is that the footprint is large enough to cover the entire park in one shot, in one scene. And also the geometric calibration and the geolocation of the pixels for these data sets is really outstanding in its accuracy. And that's really also really important.
So have you found anything surprising or interesting in monitoring the thermal features of Yellowstone with remote sensing?
Well, yes, I have. I was sitting in my office looking at a Landsat 8 nighttime thermal infrared data. It was data that was acquired in April 2017. And I was looking at it and I was comparing previously mapped thermal areas to warm spots that were detected with the Landsat 8 thermal data and matching them up. And I noticed this big blob of bright, warm pixels that didn't really match any previously mapped thermal areas. So I figured, well, maybe it's a lake. Sometimes in the spring when things start to warm up, thawing lakes can look like thermal anomalies because thawed parts look warm at night compared to the still ice-covered, snow-covered places. But no, it wasn't a lake, it was land. And so I looked at some recent high-resolution visible data, and sure enough, it was a pretty good-sized thermal area with bright, hydrothermally altered soil and a bunch of stressed, dead, and dying trees. And I thought, how come nobody noticed this before? Well, it's in the backcountry. It's not near any trails, so it's doubtful that anybody had ever stumbled upon it before. And it was also because it was new. Again, looking at archived data going back to the 90s, this area was a forest, a healthy forest with a thick stand of trees. And it wasn't until the early 2000s that you start seeing stressed and then dying trees and a tree kill area that started to grow and grow. And by the mid-2000s, you started to see a thermal anomaly there. And the area grew to about 8 acres in size. That's about 4 soccer fields. I like to use soccer fields as my unit of area. And so by around 2015, it was the size of about 4 soccer fields or 8 acres. And so I could have found it sooner, but Yellowstone's a big place and it just takes time to investigate all the subtle details and subtle changes that you see in the geothermal system. So as I systematically go through more and more data to assess and update these thermal area maps, I may find more places like this, more newly emerging thermal areas.
It seems exciting.
Yeah, it was really cool.
So just to be clear, the emerging thermal area was killing off the trees. That's why you were seeing
the heat was killing off the trees. Mm-hmm. And it's not the first or only time that's ever happened. There are a number of other places where there have been large tree kills due to a new thermal area popping up. That's one of the intriguing things about Yellowstone. It's how dynamic the thermal areas are. Thermal areas can heat up, they can cool down, they migrate as fluids find new pathways to the surface, and sometimes new thermal features appear, sometimes quietly and sometimes with a bang. And because Yellowstone is such a dynamic place, it's important to try to figure out what causes these changes, because these changes may be related to other processes, maybe natural seasonal cycles of groundwater recharge, maybe changes in the magmatic volcanic system that could be related to cycles of ground deformation or swarms of earthquakes, changes in the hydrothermal plumbing system, or they may be related to human activity. So that's one of the reasons we look for changes.
So what intrigues you about Yellowstone? You've worked with it for a while, it sounds like, and still seem to enjoy it.
Yeah, I do enjoy it. Yellowstone is a long dormant but restless volcanic system. It's basically doing everything you expect an active volcano to do except erupt. And it hasn't had a volcanic eruption in about 70,000 years, but it still has lots of earthquakes, significant ground deformation. The ground moves up and down, magmatic gas emissions and heat emissions through this very large geothermal system. And like I said before, it's the largest concentration of geothermal features in the world. And this geologic restlessness, which at almost any other volcano would be alarming, this is the norm for Yellowstone. This is just what Yellowstone does. The hydrothermal system sometimes displays really spectacular changes on a local level, but that's just Yellowstone being Yellowstone. And I find that intriguing and kind of amazing.
Absolutely. Greg, is there anything else our listeners should know or realize about using remote sensing to monitor Yellowstone?
It's pretty easy to find a lot of hype about Yellowstone on the internet. There are a lot of exaggerated claims and misinformation. You don't need to exaggerate Yellowstone to make it sound cool or amazing. It's amazing just as it is. And so the best place to get information about Yellowstone really is the Yellowstone Volcano Observatory website. If you ever have any questions about what's going on at Yellowstone, that's the place to go. That's the place to start.
We'll now hear more insights about Landsat from Terry Sohl, who is the head of the Integrated Science and Applications branch at EROS. Terry, what are some other uses people have found for Landsat's thermal data?
One of the most basic is something that touches on a lot of the projects that use Landsat in the building, and that is the use of the thermal data along with the optical to get a good cloud mask. So, a lot of our approaches use Landsat data depend on cloud-free pixels. And we don't need cloud-free scenes, but we do need to identify which scenes are contaminated with clouds and which ones are not, both clouds and cloud shadows. And most of the algorithms that can do a really good job of that really rely on the simultaneous acquisition of both thermal data and optical data. And that's really what makes Landsat unique. It's the one instrument that allows us to collect thermal and optical at the same time. And it's really critical for us to eliminate those clouds, and that supports a lot of the projects across the building. A good example of that is the National Land Cover Database. And so for the National Land Cover Database, we are looking literally through every cloud-free observation throughout the Landsat archive, going all the way back to 1984. And, having something like Landsat and having an algorithm that's able to identify those cloud-free pixels, which we do, is really vital for that project. And that's something that only Landsat can provide.
And then there are other uses too, right? Like evapotranspiration?
Yeah, so thermal data from Landsat is something that's really critical for helping us to evaluate evapotranspiration and agricultural water use. If you think of the Earth's surface and that balance between the energy that comes in from the sun and the energy that's radiated back out from the land surface, that's really dependent upon a lot of physical factors about what's going on at that land surface interface. And the thermal data is really valuable for characterizing one component of that, and that's water use by plants. And so evapotranspiration, the combination of both evaporation and transpiration from plants is something that has a cooling effect on the local landscape. And so if you think of two areas or two plots of land side by side, one that's dry versus one that's moist and is experiencing both evaporation and transpiration from plants, it's going to be cooler in that area where the wet area on the landscape is. And thermal data from Landsat is really great in terms of helping to identify those thermal balances and the impacts of water use and water availability.
So that brings into the picture things like irrigation, how much water is used with that.
Yeah, so EROS is involved in a project called OpenET, and OpenET, in our partnership with NASA, with the Desert Research Institute, and with several different academic organizations, is a good example of how we can use evapotranspiration and the thermal band to help agricultural producers. So from an agricultural producer perspective, they're interested in having the best bang for the buck in their use of water and having the highest productivity from their agricultural lands. And having evapotranspiration is something that allows them to look at water use. It allows them to know when areas are needing more water for plants that may be stressed. And it also helps them save money. They can look at ET as a product, look at water use by plants, and also know that if they have lands that don't need to be irrigated, they can save a little bit of money. So, it's something that is really valuable from the agricultural community perspective.
So, Terry, how valuable would you say Landsat is to our understanding of heat on the Earth's surface then?
It's a unique instrument, and you can recreate Landsat data in aggregate from other systems, collecting optical and thermal from different sensors and trying to, put those observations together to recreate what Landsat provides. But there are two factors that Landsat has that aren't going to be touched by that kind of approach. First of all is just the data quality. Landsat is still the gold standard, both from a calibration perspective, from a radiometric standpoint, and from a geometric standpoint. And that's really valuable from a scientific perspective, particularly if you're trying to identify change over time. Those subtle changes over in time are really captured well by Landsat. But the other component that's really valuable is that simultaneous observation. When you're trying to tie the energy balance for something like an ET to what's happening with the optical and the thermal data, you really need those data to be collected, not even minutes apart, but within just a second or two of each other. And that's the big advantage of Landsat, is that simultaneous collection.
Thank you, Greg and Terry, for joining us for this episode of Eyes on Earth, where we have explored the use of thermal remote sensing, especially Landsat data, to monitor Yellowstone National Park's unique features. And thank you to the listeners. Check out our EROS Facebook and X pages to watch for our newest episodes. And you can also subscribe to us on Spotify and Apple Podcasts. This podcast is a product of the U.S. Geological Survey, Department of the Interior.